Good afternoon to all of you, and welcome back to the counseling session of the course BMTC 131. And today we are going to focus on the block 4, and particularly block 4 is totally dedicated to the applications of differential calculus. So today we first focus on the definition of the first derivative test. So as you can see in the PDF that was presented on your screen. So here the first derivative test, basically this first derivative test is used to test if function is increasing or decreasing at a certain point. Now look at the particular figures which are drawn in the figure number 22 that was presented on your screen in PDF. So in that particular figure, we may point out that we have three different patterns of figures are there. So here, in the first pattern, look at the point B. Here in point B, the tangent is parallel to x-axis. So here we can say that the first derivative of the function will be 0. If we slightly move to the left of this point B, then the first derivative of the function at the left side of the point B is 0, it will be positive. Similarly, if we turn slightly right to the point x0 in the right hand side, then here the slope will be negative. So in this way, the pattern, if we look at the pattern of sign change, here the sign changes from positive to negative. So whenever we find this type of situation, sign is changing from positive to negative, we have a relative maximum of the function at that certain point. Similarly, if we analyze the second figure in B, now look at the point C here. So at that exactly point C, if we are going to calculate the tangent, and clearly you can see that the tangent will be obviously parallel to x-axis. So we can also conclude that when a tangent is parallel to x-axis, clearly you can say that the derivative of the function at that point will be a 0 or critical point. So here the same process, if we look just left of this point C, or we can say that it is x0, the slope will be here negative. That means the f dash x0 value will be negative, but slightly in the right hand side of the point C or x0, the slope of the first derivative of that point will be positive. Now look at the pattern of sign changes of the function at the point from left to right. So when we move from left to right to the point x0 or C, sign it changes from negative to positive. So whenever this type of pattern of sign changes occur, conclusion will be the function have a relative minimum at the point x0. So that is the second point of discussion. Now look at the third one. In third figure, we can clearly see that at the point E or at the point F, if the point E or F, if we choose the left side of the points, then in first curve, the value of the slope is positive. If we also move towards the right hand side of the point, also the slope is positive. That means sign does not changes here in this particular figure with respect to the upper curve. Similarly, if we look the lower curve that was drawn in the lower part of the figure C, so here it also the value of the slope of the first derivative of f at the point x0 is negative. So that's why if we move slightly right hand side of the point, then also the first derivative at the point is also negative. That means sign does not changes near the points of x0 when we are moving from left to right. So the conclusion will be made here. There is no extremum. That means the conclusion is not an extremum will be found at the point x0 when this type of situation occurs. That means the sign of the function of the first derivative does not changes in an open interval from left to right. So that's why the conclusion will be no extremum. That means we do not have any relative maximum or relative minimum value of the function at the certain point. Now the same will be discussed with the help of this example. So look at that example. Example number 14. In example number 14, the function is given in the form of x minus 2 sine x. And here the interval is given 0 to pi by 2. That means the function is defined over the interval 0 to 2 pi. 0 to 2 pi. And now let us determine whether the function attain relative maximum or minimum or neither of any one. So for this investigation, first we have to calculate the first derivative of the given function. That was calculated here. F dash x equals to 1 minus 2 cos x. Then we are equating the same to 0, and by solving this equation we will find the value cos x equals to 1 by 2. That means the value of x will be pi by 3 and 5 pi by 3, and these are the two values which lies in the interval of 0 to 2 pi. So now these are the 2 points are our focus point of discussion. That means at these 2 points the function may have attained relative maximum value or relative minimum value or neither any one. So let us look at the table. So in the table it has been clearly mentioned that 0 to pi by 3. That means in the left hand side of the first one, the interval is of interval from 0 to pi by 3. That means there is a left interval of the point pi by 3. And here the sign of f dash x is positive. So we have to ensure the sign by substituting any value of x between this interval 0 to pi by 3, and that is negative. So here we can conclude that the function is in decreasing form. Now look at the other side. So here in other side of the interval of the point pi by 3 to 5 pi by 3. So this is the n also open interval 5 pi by 3 pi by 3, and here if we choose any value between this interval and substitute in the value of f dash x, first derivative of f dash x, and we will get here positive value. That means it is the increasing sign of the function. So now if we look at the pattern of changing sign, so here the first derivative of the function is changes from negative to positive if we are moving from the left of pi by 3 to right of pi by 3. So that's why we can give a conclusion there is a relative minimum at x equal to pi by 3. So similarly, the same process can be done with the point 5 pi by 3. So similarly, to draw the conclusion for the point 5 pi by 3, we have taken here another open interval from 5 pi by 3 to 2 pi. So again, the same process we have to add up. We have to choose any point between this particular interval, and the value of the function will be here negative. Negative means it is decreasing sign. So now again, if we look, the pattern of sign changes from positive to negative, the pattern of sign of first derivative of f changes from positive to negative at the point x equal to 5, 5, 8. So therefore, here we can give a conclusion that the function must have relative maximum at the point 5, 5, and 3. So this is the simple procedure to test a function whether it is attained relative maximum value or minimum value at a certain point by using first derivative test. So now we are moving towards the next one, that is all about the second derivative test. So if you have any question, then please. Otherwise, we are moving towards the next one, that is in the page number 57. So let us open page number 57, and here we have to discuss about the second derivative test to find the relative maximum or minimum of a function at a certain point. So this particular second derivative test is quite simple and easy. So now look at the statement of this second derivative test to test a function attain its maximum value or minimum value at a certain point. So here the statement goes like that. The function, we have chosen here, let a function f and its first derivative at x0 is equals to 0. That means we are saying that the function has a critical point at the point x0. And also you can say that its second derivative exists on that particular point containing an open interval, the point x0. So here, after calculating the second derivative of the function at that point x0, if the value will be positive. So when the value of the second derivative of the function of the point x0 is positive, then conclusion is that the function attains relative minimum value, it is relative minimum value at x equal to 0. Now look at the second point. Here in second point, the condition is just opposite. That means if the second derivative of the function at the point x0 is negative, then conclusion will be the function attain its maximum value, and the maximum value will be relative maximum at the point x0. And this particular process is quite simpler as compared to the first derivative test, because here we does not have to observe any sign change from left to right, but we have to just calculate the second derivative of the function at that point, and we have to observe the positive and negative value of that particular point. And according to that one, we can give a conclusion about the relative maximum and relative minimum of the function at that certain point. So now let us discuss the same with the help of an example. So look at that example number 15 is page number 58. So here the example is given a function, and the function is equals to 2x plus 3 by x, and the function is defined for all x, that means for all real number but x not equals to 0. That means the function is defined for all x except at 0. And here the question we are going to find out that or investigate that the function attains its maximum value or not at the critical points. So first we have to calculate the critical points by assigning the first derivative of the function f dash x equals to 0. So now first we calculate the first derivative, that is 2 minus 3 by x square, and equating to 0 we get two values in the form of plus minus root over of 3 divided by 2. So these are the two different values at which the function may attain relative maximum or relative minimum value. Now to ensure that one, let us calculate the second derivative and f double dash x equal to 6 into x to the power use the value of x, that is the power of 3 by 2. So here in the negative of root over of 3 by 2, the value is negative. Second derivative will be positive. The conclusion will be negative value. Then you can say that the function attains its maximum value at that point. So now slow है जाओ थोड़ा. Online sir ଏମିତି ଅସୁବିଧା
ଏ ଆପଣଙ୍କ ଘରେ ଖାଲି ହଉଛି ଏଇଠି ବସିଲେ ହଉଛି ନା
अरे इथे
ମୁନୁ
डायरेक्टली
ମୁନୁ ମ୍ୟାଡାମ ତ ବଢିଆ ମୁନୁ 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 କରି
सुबह तो की था
Hello, do you have any question?
Good afternoon.
Hello.
Good afternoon, sir. Good evening, sir. Sorry.
ପୁଣି ପଳେଇଲା। ସୁନିତ ସର୍ବତ ସେମିତି କରୁଛି। ଏଟାରେ ଆଉ ନଉନି ନାହିଁ ପ୍ରଥମ ଦିନ
ଅଫିସ
ଏକା କଥା ଯୋଉଠି ହେଲେ ବି
ନେଟୱାର୍କଟା ସେ
ଆଚ୍ଛା ଆଚ୍ଛା ଯିବା ଚାଲ
ଯିବା ଚାଲ।
अरे प्रेजेंट कर दीजिए। हेलो अरे सर So we are discussing the statements of Rolle's theorem. So according to the statements of Rolle's theorem, let us focus on the statement. It was given in the page number 61. So now look at the statement of the Rolle's theorem. So here the function is given defined over a closed interval, and the function is continuous, f of a equals to f of b, then there is a sum c in the open interval ab such that its value, the first derivative of the function f at that point c, must be 0. So that is the conclusion of this Rolle's theorem. So whenever these three conditions satisfied, we can say that there is a point C inside the open interval AB, and such that S equals to 0. So here, to verify the Rolle's theorem, let us discuss for the example number 17. Not. So now, to verify the Rolle's theorem, we have to ensure that the function must be continuous in the closed interval from 0 to 2 pi, and as we know, as we have idea, we want a function sin x is continuous in the period of 0 to 2 pi, and also it is differentiable in the open interval 0 to 2 pi. The conditions are satisfied of the Rolle's theorem. Now look at the third condition of the Rolle's theorem, that is the function value at the first point of the interval and the function value at the second point of the interval must be same. So here f of 0 equals to 0 and f of 2 pi is also 0. That means all the three conditions of the Rolle's theorem are satisfied, and we can give a conclusion here. So now, to draw a conclusion, we have to ensure that now the point C must be lies in the interval 0 to 2 pi. So let us solve the equation. That means f dash c equals to 0, and now f dash x equals to cos x, and f dash c will be cos c. Now equating this expression equal to 0, cos equal to 0, and we will get the value of c lies inside the open interval 0 to 2 pi, and the values are pi by 2 and 3 pi by 2. So clearly you can see that now these two values at pi by 2 and 3 pi by 2, the function 3 pi by 2 must lie inside interval 0 to 2 pi, and it will be clearly 0. That means it is satisfied the conditions of the Rolle's theorem. Now let us discuss the next point, and the next point is about F5. So let us moving towards page number 65. Yeah, in page number 65, we can see the statement of the Lagrange theorem, Lagrange mean value theorem, and it is states that let a function f be continuous function on a closed interval ab, and let f be differentiable in the open interval ab, then the Rolle's theorem is, in Rolle's theorem we assume that f of a equals to f of b, because when f of a equals to f of b, then the numerator will be 0, and in that case f of c f dash c will be 0. So now we can conclude that Rolle's theorem statements all about the Lagrange mean value theorem. Now we have a graph of function f, and look at the point C and f of c, the function value. So similarly, here the function is defined over a closed interval AB, and it is continuous and differentiable in the closed interval AB. Then Lagrange mean value theorem such as f dash c must be equals to f of Lagrange mean value theorem. So now let us moving towards the page number 80, and here in page number 80 we have to discuss about the concavity of a function. So here in concavity of the function, look at the definition carefully. We analyze the figure, then we discuss about the mathematical conclusion procedure about x. Look at the figure number 2 in page number 80, and here in the first figure, look at the chord. The chord is light, which we discuss the condition of chord. Here this chord is light just below the car F. So that's why we can say that the curve is, or the function is concave downward. Concavity test of the function. So here the first condition is, then the conclusion will be given to the graph is concave upward. So if it is positive, then it is concave upward. If it is negative, then the graph will be concave downward on I. So here, now let us moving towards the equation of tangents and normal to the curve that was in the page number 91. So let us move to the page number 91, and here in page number 91 we are going to discuss about the tangent, equation of tangent and normal to the curve. So look at that one. To find out the equation of tangent or the slope of the tangent at the point x0, y0 and slope of the normal at the same point x0, y0. So that will be like that. So first we calculate the first derivative of the function, that is f dash x0. Now this f dash x0 will be always represent this x0 will be always represent the slope of the tangent line, whereas present minus 1 by f dash x0, this will represent the slope of the normal at that particular point. So now because as you know in two-dimensional geometry, slope is always turns negative, that is minus 1 x0, that is dash x0, and that is the slope of the tangent line, and we are represent here minus 1 divided by f dash x0, and that will be the slope of the normal line. Because if we multiply this two, then once we get the slope of the tangent and slope of the normal, now let us moving towards the next unit, that is unit number 15, that is all about the asymptotes, and it will be in the page number 117, 117. So let us move towards. If you have any question, then please. Hello. Hello, Priyanka Padhi. Am I audible? Can you hear me? Hello. The asymptotes. And here the structure of this particular unit of asymptotes it goes like that. Asymptotes, the definition of first introduction of asymptote, what are the asymptotes and how we can define asymptotes. Then the calculation procedure of slant asymptote if the asymptotes are non-parallel to coordinate axis. Then the summary of this particular unit over the asymptotes. So now to analyze the same, look at the figure in figure number 1 in page number 118. So let us move to the figure. is gradually decreasing towards x-axis, and also we very clearly found that this difference between the curve and difference between the x-axis is gradually decreasing, at it will be zero at infinity. That means we can say that yes, then the straight line is said to be an asymptote. So, in other words, we can also define like that: an asymptote is a straight line. An asymptote is a straight line, and that will be tangent to the curve at infinity. So, in the same way, also the axis will toss the curve at positive infinity, and similarly, the negative curve at negative infinity. So here, both the axes, x-axis and y-axis, are the asymptotes to the curve in the figure number 1. So that idea has been used to define the formal definition of a function if f of x tends to infinity or minus infinity when x is adopted to define the definition of the vertical asymptotes. So here, in this example, also we can see the examples of vertical asymptotes clearly. These lines are the asymptotes to the car, because the dotted line will touch the car at, and the dotted line, that means the straight line, and the car is gradually decreasing asymptotes to the car. Now let us discuss about the working procedure. How can calculate these vertical graphs and horizontal graph of the function. First, we have to equate the highest degree term of x, and we have to. So let us discuss the same in page number 126. So let us move to the page number 126, and we are discussing about the working rule to find out the asymptotes parallel to x-axis and parallel to y-axis. So look at this example. If we are looking at particular example, now if we simplify the equation in, in that form, equation form, so we can represent in the form of a square y square minus b square x square minus x square y square equals to 0. Now from this expression, x square is the highest degree of the variable x and y square is also the highest degree of the variable y. Now to go here and minus y square. So we are going to equating and that will be y square plus b square equal to 0. And when you are going to solve that one, it will be y equals to plus minus ib. So here we have two lines, two imaginary lines, y equal to plus minus I x axis. So similarly here we can equating the highest degree, we first take the highest degree of f and x a square. So x square minus x square equals to 0, and we get here the value of x, that is x equal to plus minus a, or clearly it will represent two different lines, and these lines will the equation of asymptotes. These are the next focus point of discussion, that is all about the oblique asymptotes or slant asymptotes when parallel to axis. That means when asymptotes are non-parallel to coordinate axis, then what are the procedure to calculate the same? So here, look at the figure. In that figure, we clearly observe the dotted lines. So here, dotted lines are clearly non-parallel to the oblique asymptote or slant asymptote. We have a simple definition here. The definition goes like that: a line y equal to mx plus c. So this is the equation of straight line in slope intercept form, and this kind of line will be oblique asymptote or slant asymptote when the graph of the function approaches to infinity. F of x minus x plus is 0. That means it satisfies the definition or the condition of the asymptote. So now let us find the slant asymptote of the curve given here. Y use the simple procedure calculation, that is limit x tends to infinity y by x. So here y means the given equation of the curve. We substitute, then we calculate the limit, and the limit will be here 1. So that means we can calculate easily the value of a that equals to 1. And similarly, we can calculate the value of c. We know the value of m, so that is substituted here. We have the value of function, and then we are using the limiting value of the function, and we got the value is c equals to 0. So in this way, we can calculate the value of m by using the relation y by x, and we can calculate the value of c by using the relation y minus. We can represent slant asymptote as y equal to mx plus c. So mx plus c, m equals to calculation procedure to find out the slant asymptote. And finally, in the last part of this particular module, the last unit is about the curve tracing. So let us normal, asymptotes, period, increasing, decreasing, these kind of particular function. So now let us move to the page number 138. So here in page number 138, it is the tracing of a curve, tracing of a curve form. So look at the first function, look at the first condition to trace the graph. So here the first condition is that we have to simplify the expression. So if possible, we have to simplify the given function. Now, after simplification, we end up in xy plane or coordinate plane, and then we have to find out the periodicity. That means if the function is periodic function, then what will be the period of the function? If we know the period of the function, then according to that one, again we have to mark the xy. This it may be x-axis or y-axis, or it may be any slant or oblique line. Then also we think about y-axis, also we think about y equal to x. So these are the figures which explain symmetric about x-axis, symmetric about y-axis, symmetric about origin, and symmetric about the line y equal to x. Now, some conditions are also described here. In the first condition, you can find that now point of intersection. If the curve intersects these points. Now the sixth one is point of discontinuity. If the function have any point of discontinuity, then we have to find out the point, and we have to locate the point in that particular xy plane. Now, intervals of increasing and decreasing function. According to the first derivative test or second derivative test, locate the interval according to that one. Now the quantitative points. Then also you have to ensure that the function attains maximum value or minimum value or does not attain any relative maximum minimum value at certain points of the interval. And finally, we have to move to the 10th point, that is tangent and normal. We have to also investigate about the tangent and normal to the curve at different point asymptotes. Then 11th point is asymptotes. Then in 11th point, we have to investigate about the asymptotes, whether the asymptotes are present or not. If they are present, then what will the equation with asymptotes, whether they are parallel to x-axis or y-axis or parallel to any, not parallel to any other axis, that means the slant asymptotes. Then singular points, if any, then you put examples are given below, and we have to investigate one by one point, and according to that one, then finally draw. I would like to thank all of you who have joined in this session of block 4, and today we will discuss about the applications of differential calculus. So, thank you, and we conclude the session.